Hello, beautiful viewers. You are welcome once again to another fascinating math video. In this video, we shall be looking at the application of mathematical induction in solving the products problem. Actually, we are given a product equation and we are required to find the value of x. I would like to add that I render an online mathematics tutoring service. So if you're interested in such a service, be very free to get across to me. And also, if you draw value from this video, please ensure to click the like button and share. Please help me by extending this video to others. The more you like and share the video, it will get to others and thereby promote my page. Please do me a favor to like and share the video. And also, message me directly if you're in need of an online mathematical tutoring service. I also help in assisting in assignments and tests, project work and research. So if you're in need of any of these services I've mentioned, be very free to get across to me. All right, so let's get over to the solution of this particular problem. Over here, we are required to find the value of x in this equation. Now, I will explain the symbol, the meaning of this symbol. Let's look at the solution together. Solution. This symbol you see here is a product symbol. You know, this symbol sigma is a summation symbol. Whenever we write sigma I, from I range from 1 to n, this is a shorthand way of writing the expression 1 plus 2 plus 3 plus and so on to plus n. The same way, if we write this pi from I to n, we mean 1 times 2 times 3 times 4 times and so on to n. That is the meaning. So this pi symbol here stands for products, all right, the product expression. So we are required to find the value of x. We are required to find the value of s in this equation. Now, to get the value of s, we must get the product of this expression, this particular expression over here. We must get the product of it. Now, how do we get the product? First of all, we should consider this scenario. We can say consider pi ranging from 2 to n, all right, of 1 minus 1 over I to the power 2. And if we should interpret this is equals to writing 1 minus 1 over 2 squared, because I starts from 2, multiplied by 1 minus 1 over 3 squared, multiplied by 1 minus 1 over 4 squared, and so on until you get to 1 minus 1 over n squared. So we want to get a simplifying expression for this. All right. Now take note that 1 minus 1 over 2 squared multiplied by 1 minus 1 over 3 squared multiplied by 1 minus 1 over 4 squared until you get to 1 minus 1 over n squared can be equally written as, now if you observe carefully, the expression in the parentheses is a difference of 2 squared. In each of the parentheses, each of the expression is a difference of 2 squared. So writing them in the other format, we shall have 1 minus 1 over 2 multiplied by 1 plus 1 over 2. Then we have the next to be 1 minus 1 over 3 multiplied by 1 plus 1 over 3. All right. The next we have 1 minus 1 over 4 multiplied by 1 plus 1 over 4 until you get to 1 minus 1 over n multiplied by 1 plus 1 over n. So we have this expression at hand. Now, taking the difference expression separately, we shall have the result as 1 minus 1 over 2 multiplied by 1 minus 1 over 3 multiplied by 1 minus 1 over 4, and so on like that. Let me remove this. And so on like that until you get to 1 minus 1 over n. All right, we have this. is the first separation. The second separation will be 1 plus 1 over 2 multiplied by 1 plus 1 over 3 multiplied by 1 plus 1 over 4, and so on until you get to 1 plus 1 over n. Can you see that? Please don't forget to like and share this video if you draw any value from it. Help me to promote this, please. I'm on a plain side. Help me. We help each other, all right? As you are gaining value from this, still help me to like and share it. Thank you very much as you do that. So let's continue the problem. Now we have this expression here at hand. Now we want to look for a simplifying expression for each of these. So I can call this equals to, let me call it PZ. All right, where P is the difference expression, that is 1 minus 1 over 2 multiplied by 1 minus 1 over 3 multiplied by 1 minus 1 over 4 until you get to 1 minus 1 over n. All right, you can see that. The end, my z is defined similarly, that is 1 plus 1 over 2 times 1 plus 1 over 3 times 1 plus 1 over 4 until you get to 1 plus 1 over n. So we want to look for a simplifying expression for P and for Z. And having done that, we have to prove that the simplifying expression is true, is generally true. And we shall use the implementation of mathematical induction to establish it. So let's start with the first, that is P. Let's start with the first P. Now observe something here, that for P, now let's look for simplifying expression. That is, we look for simplifying expressions for P and Z. All right, for P and, sorry for this. Oh, it's a great mistake. This line I drew here. Let me remove it. Sorry for this. We are good to go. So we look for a simplifying expression for P and Z. Now for the first, let's look for P. For P. Now you know P is equals to 1 minus 1 over 2 multiplied 1 minus 1 over 3 multiplied 1 minus 1 over 4, and so on to get to 1 minus 1 over n. So let's take the product of the first two terms. In this case, we have okay, even before that, let's go. 1 minus 1 over 2 can be seen as times 1 minus 1 over 3 is equal to writing 1, that is, we have 1 over 2, that is, when you simplify this expression here in the parentheses, you get 1 over 2, all right? Then times 2 over 3, and this will breaks down to 1 over 3. Can you see that? Then let's take more term. Let's take more term to verify this. Let's consider 1 minus 1 over 2 multiplied by 1 minus 1 over 3 multiplied by 1 minus 1 over 4 and see the result. This is equals to writing. Now already this expression here has the result as 1 over 3. So I can write this entire expression as 1 over 3 multiplying 1 minus 1 over 4. Then this can be written as 1 over 3 times 3 over 4. You see that the result is once again 1 over 4. All right. So let's take we have taken how many expressions, how many terms? 1, 2, 3, 3 terms. So let's take the one more term and see the pattern that we play out, whether we have a beautiful pattern. So we have 1 minus 1 over 2 multiplied 1 minus 1 over 3 multiplied 1 minus 1 over 4 multiplied 1 minus 1 over 5. Let's see what will happen. Now this is equals to writing. Now already this expression will have a result for it as 1 over 4. So I can write 1 over 4 multiplied. This one here will simplify it to 4 over 5. And we have our answer as 1 over 5. All right. So in general, we see we can make an we can extrapolate to the result. We can now say, therefore, my P, which is equals to 1 minus 1 over 2 multiplied 1 minus 1 over 3 multiplied 1 minus 1 over 4 until you get to 1 minus 1 over n. The answer, the result of this should be 1 over n from the pattern we've seen playing out. You know, for these two terms we took, we have 1 over 3. For these three terms we took, we have 1 over 4. For these four terms we took, we have 1 over 5. So it is very logical to suppose that the product of the n terms will be 1 over n. So, but we have to prove this statement, whether it is true. All right, you know, this is just a statement. And how do we prove it? We want to apply the instrumentation of mathematical induction to establish that this is true. In mathematics, you don't just make statements based on patterns. You have to prove that that statement you made is generally true by trusted implements such as mathematical induction. That is how, if you are studying pure maths, we don't take results like that based on the fact that a pattern is playing out. A pattern may play to a certain extent, but may fail to play beyond it. So how do we know? How are we sure that it will not fail in the long run? So to avoid that, we establish it by trusted tools, such as mathematical induction in this case. The reason I want to use mathematical induction is because this statement is about the natural number, that is the positive integers. Mathematical induction is strictly applied to positive integers, problems that involve positive integers, all right? So let's establish this problem that it is generally true by the usage of mathematical induction. I'll add more page to our work now. So now we have that 1 minus 1 over 2 multiply 1 minus 1 over 3 times 1 minus 1 over 4 ranging to 1 minus 1 over n. We have the result to be 1 over n. This was our supposition, the hypothesis. So we have to prove this, whether it is so. Now, this is true for n bigger than or equals to 2. Take note of that. It is true for n bigger than or equals to 2. So we want to prove this. We can say let A be the set. Let me call this, okay, we are good to go. Be the set of all positive integers for which 1 minus 1 over 2 multiplied 1 minus 1 over 3 until you get to 1 minus 1 over n equals 1 over n. So let A be the set. We are defining a set now, and we are defining it as follows: that A should be the set of all positive integers for which this statement is true. All right. So let's show that the number 2 is in the set A. How do we show that? When n is 2, we shall have that 1 minus 1 over 2, that is the first term, is equals to 1 over 2. All right, and it's true. 1 minus 1 over 2 is it not equals to 1 over 2? It is so. That means that this implies that 2 is an element of the set A. So we've established that already. And the next stage is the supposition stage. So we can suppose that that K is an element of the set A. That is, the statement is true for a positive integer K. All right? That is, we have that 1 minus 1 over 2 multiply 1 minus 1 over 3 until it gets to 1 minus 1 over K is equals to 1 over K. We suppose that this is the case. And let's call this a star. All right? Then we shall prove that this supposition will imply that the statement is true for a positive integer K plus 1. We shall, by this supposition, establish that the statement is true for a positive integer K plus 1. Now, we can say consider the expression, which is 1 minus 1 over 2 multiplied 1 minus 1 over 3 until you get to 1 minus 1 over K plus 1. 1 over K, then 1 minus 1 over K plus 1. Can you see that? Now, we can create this latter expression from star by multiplying both sides of star by 1 minus 1 over K plus 1. So if we multiply both sides of star by 1 minus 1 over K plus 1, we shall obtain this expression that we have currently. So On multiplying both sides of star by 1 minus 1 over k plus 1, we have the following. We have 1 minus 1 over 2 multiplied 1 minus 1 over 3 until you get to 1 minus 1 over k. Then multiply this by by 1 minus 1 over k plus 1. That was what I said initially. And that is equals to, since we are multiplying both sides, we apply to this other side also. We have 1 minus 1 over k plus 1. Can you see that? All right. So on doing so, we have the result as 1 minus 1 over 2 multiply 1 minus 1 over 3 until it gets to 1 minus 1 over k. Then we have 1 minus 1 over k plus 1. Now, multiplying the left-hand side, rather simplifying the right-hand side, we have 1 over k multiply k plus 1 minus 1 over k plus 1. This is just simple manipulation of fractions. Can you see that? Then minus 1, we cancel out this. We are left with k. We also cancel out this. So we have here as a result, we are having 1 over k plus 1, which was the assertion, which was the proposition, but this time around, it is a proposition for k plus 1. So in other words, our assumption in star has led to an implication, which is a proposition, but this time around in k plus 1. So we can say, let me call this a star star, all right? Let me call this star star, for example. So we can say, therefore, star implies a star star. That is, the statement, the supposition has implied that the statement is true for a positive integer k plus 1. In other words, that is, k being an element of A has implied that k plus 1 is also an element of A. And by the axiom of induction, it follows that, therefore, n is an element of A for all n being elements of the set of positive integers. So these have shown that the statement is true for all n that comes from here, and n is bigger than or equals to 2. Don't forget that. All right. So for all n bigger than equals to 2, this statement is indeed true. So we have established the fact that the statement is true for all n bigger than equals to 2. So this makes it more solid instead of just mere extrapolation to the result without any proof. Because somebody may question you, how are you sure this is true in the long run? In time indefinite, will this continue? But by this proof process, well, it has shown that it will continue in time indefinite. That is, on the long run, it will be true. So it's good to establish a claim by proof process in mathematics. So we're done with establishing that P is true for all n bigger than or equal to 2. So let's go over to Z. We are done with P. Let's go over to Z. What is Z? Z is 1. Look at Z here. Let me illustrate. Can you see that? Look at it here. This is Z. So let's establish that this will be true. First of all, let's look for a simplifying expression for this. Let's look for a simplifying expression for this one first. So Z is equal to 1 plus 1 over 2. The next we have 1 plus 1 over 3 until you get to, okay, let me add more 10. 1 plus 1 over 4 until you get to 1 plus 1 over n. All right. Now, this can be written as on simplifying this one here, we have 3 over 2. Can you see that? The same thing, this we have 4 over 3. Then this we have 5 over 4. So note that the next term will be 6 over 5. All right, and so on until you get to simplifying this expression here, we have n plus 1 over n. And this can be further written as 1 over 2 brackets 3 multiplying 4 over 3, 5 over 4, 6 over 5 until you get to n plus 1 over n. Please follow what I'm doing, very, very important. Now, you can see that this 3 will cancel out this 3. you'll be left with 4. 5 will cancel out 5. You'll be left with 6. So on the long run, an n in this position will cancel out this denominator. So we'll be left with n plus 1. In other words, the result of this on simplification should be n plus 1 over 2. Can you see that? But we have to prove this. This is just an extrapolation to the results. We have to prove this by mathematical induction also. So we can now say, therefore, my z, which has the expression as 1 plus 1 over 2 times 1 plus 1 over 3 times 1 plus 1 over 4 until it gets to 1 plus 1 over n is equal to n plus 1 over 2. But this is not a satisfactory statement. It has to be proven by using mathematical induction. All right? So let's prove it and see whether it's true. This statement is true for all n bigger than equals to 2, but we have to prove it. It is so. So to do that, we say let B be the set of all positive integers for which this statement is true. So we can say let B be the set of all positive integers for which Z holds. So we can say that, all right? So please follow tightly, follow closely. We're almost there at the results. Now we have this at hand. So let's show that 2 is an element of the set B. Let's show that. Now observe that 1 plus 1 over 2 is equal to, now when n is 2, put 2 here, you have, put 2 in this right hand side, you have 2 plus 1 over 3, over 2 rather. And that is the case because 1 plus 1 over 2 is equal to 2 plus 1 over 2. Can you see that? So that means that the element 2 is an element of the set B. So we've shown that. The next we go to the supposition stage. We can say suppose that K is an element of the set B. Now if we suppose this, then we shall make the statement. We can say therefore that is 1 plus 1 over 2 multiplied 1 plus 1 over 3 until it gets to 1 plus 1 over k is equals to k plus 1 over 2. So this is supposition stage. Let me call this a star, star, star. All right, let's call it star, star, star. So we continue the work from this page. Now, next we consider the expression. Now, from this supposition, we want to establish that the statement is true for the positive integer k plus 1. So for that, we consider the expression. The expression. We have 1 plus 1 over 2, 1 plus 1 over 3, until you get to 1 plus 1 over k, then multiplied by 1 plus 1 over k plus 1. Hope you can see that. And this is the expression we are considering. Please don't forget to like and share this video if you are gaining any value from it, as it will help to extend it to other viewers. Please do me the favor of liking and sharing the video. Thank you very much for doing that. Now we are looking at this expression 1 plus 1 over 2 multiply 1 plus 1 over 3 until you get to 1 plus 1 over k plus 1. Now this expression can be derived from star 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 by multiplying both sides of star 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 by 1 plus, this expression, look at it here, let me illustrate. If we multiply both sides of this expression here, can you see that? This expression, we multiply it by this quantity, both sides, we shall derive this entire expression. Can you see that? So let's go about it. So in that case, we multiply both sides of star 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 by 1 plus 1 over k plus 1. So in that case, we have 1 plus 1 over 2 multiplied by 1 plus 1 over 3 until it gets to 1 plus 1 over k, then times 1 plus 1 over k plus 1. But don't forget, it's both sides of star 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 you are multiplying. So we have k plus 1 over 2 multiply 1 plus 1 over k plus 1. Can you see that? Now, the right-hand side we have can now be simplified as follows. We now have k plus 1 over 2 multiplied by k plus 1 over k plus 1. From whence this we cancel out with this, and we are left with k plus 2 over 2. And that is the assertion for the positive integer k plus 1. You know, when it was k, the assertion was this. Look at it here. Look at it. That is the assumption case. Now, this assumption case now led us to the statement being true for k plus 1. It gave us this expression. Can you see that? Look at it here. So because of that reason, we can say that star 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 as implied. Let me call this, let me label this as A, for example. So we can now say therefore, star 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 implies A. All right? That is K being an element of B has implied that K plus 1 is also an element of B. And by the axiom of induction, it follows that N is an element of B for all N that are bigger than equals to 2, which are positive integers. So we have proved rather that this proposition is true for all positive integer bigger than or equals to 2. So it's no longer a mere statement or a mere extrapolation to results, but we have established that on the long run it will be true. So in that case, we are very confident. Now we have two expressions at hand here. The first is this for z. Can you see that? This is the first expression for z, a simplifying expression. While the second is for p. Where is it again? P, where are you? Where are you? Where are you? Yes, P. All right, this is here. Look at it. Can you see that? So we have 1 over n for P, and we have for Z, we have n plus 1 over 2. So let's go back to our original problem. And this was the original problem. We have x multiplied the product ranging from I equals to 2 to 556 of 1 minus 1 over I squared equals to 500. We have to find the value of s. Now, to get the value of s in this case, we have to evaluate this expression. Look at it here. We have to evaluate this expression. And it's very easy. Now, the work is easy because we have derived simplifying expression. So I can now come and say, therefore, the value of ranging from I equals to 2 to 556 of 1 minus 1 over I squared is equals to, now, you know, this can be written as pi 556 I equals to 2. Then we can write 1 minus 1 over I multiplied by 1 plus 1 over I. And the result, okay, let me remove this number first and use n instead. Let me remove this and put n here to make the work simple. Now, we've observed that the results can be written as 1 minus 1 over 2, 1 minus 1 over 3 until you get to 1 minus 1 over n, all right? Remember, we have this, then multiplied by the same thing, 1 plus 1 over 2 until you get to 1 plus 1 over n, all right? And we've obtained a simplifying expression for this first expression in this square parenthesis. And what was the expression? That is p. And our value for p was, yes, p again, 1 over n, all right? So we come here and write 1 over n in the place of the expression. So we have 1 over n here times, why this one we have the value of n plus 1 over 2. Let's check it out. For z, n plus 1 over 2. Look at it here. Can you see that? So we come here and write n plus 1 over 2. And that will give us n plus 1 over 2n. So we can now see that We can say, therefore, the product ranging from 2 to 5, 5, 6 of 1 minus 1 over I squared is equals to, now the number here, the highest number here is 5, 5, 6. So we can write 5, 5, 6 plus 1 over 2n, which is 2 times 5, 5, 6. All right. So which will give us 5, 5, 7 over, we multiply out, this is 12, put down 1 carry, put down 2 carry 1, 10, 11, put down 1 carry 1, 10, 11 again. So we have this as a result. So this entire expression have this as a result. All right. So we cannot come to the original equation. What was the original equation? X times this. So we now have this, we now have a result for this entire expression here. So that is not a problem any longer. So in the place of that expression, we shall put the value we've obtained. So we can now come over here and write x times, instead of this expression now, we'll put the value 557 over 1, all right, equals to 500. So this is a very simple equation to solve. We transpose to get x, so we'll have 557x equals to 1112 times 500. And that is a very big number. Then to get the value of x, we divide both sides by 557. Therefore, x equals to 1112 times 500 divided by 557. And this is the value of x. All right, so we've come to the end, the conclusion of this video. So if you draw any value from it, please do me the favor of liking and sharing it so it can be extended to other viewers like you. All right. Don't forget that I render an exclusive online mathematics tutoring service. So if you're interested in such a service, be very free to message me. Also, I assist in assignment and tests, project work, and research. Be very free to get across to me if you are in need of this service. I have an experience, a practical teaching experience that spans over a decade now, teaching various levels from primary to high school level to undergraduate. I've been in teaching for a very long time. I'm very competent and prolific when it comes to handling mathematics. So be very free to get across to me. And I promise you, you will draw great value from a personal tutoring service. So thank you very much for your time and do really appreciate you all. Till next time.